Hi everyone, today we'll be taking a look at question 236 on LeetCode called lowest common ancestor of a binary tree. So a lowest common ancestor is defined as um, the ancestor between two nodes such that it's the lowest node in the tree such that both the two nodes that we define are descendants. And we are allowed to have a node be a descendant of itself. So for example, in this tree with the example of 5 and 1, 5 and 1 are right here, so the ancestor is 3. For example, 5 and 4, 5 and 4. Since a node can be a descendant of itself, we return 5. Cool. So to do this, let's define how we're going to find whether something is a descendant of something of another node. So to figure out if a node is a descendant of another node, we can say that if it exists in its left or right subtrees, or if it's the node itself, then we can say that it could be a possible ancestor. So, for example, let's say if we were trying to find um, 8 here and we were looking at node 1, since node 1 does have a right subtree that has the node 8, we can say that this is true. Same thing for something like 7. Since node 5 has a right subtree that contains node 7, we can say that 5 is an ancestor of 7. Cool. So how we define this then? We know that a ancestor then is true if we have three cases. One, if it exists in the right subtree. Two, if it exists in the left subtree. Or 3, if it is the node itself. Cool. So with these three conditions, we can basically write a DFS function that checks for these three conditions. And if two of them are true, that means that we found an ancestor that is true for two of the nodes that we're trying to find. Thus, that is the lowest common ancestor. So let's try that. Let's start the answer with no, just in case if we don't find anything. Write our function DFS with the node that we're working with, as well as P and Q. So if the node is null, we want to return 0. So the reason why we want to return 0 here is because if we reach a null node, we will never be able to find its, and sorry, it will never be a descendant of something else. So, oh, sorry, it won't ever be an ancestor of something else. So in this case, we can define our left and right subtrees. So we can say left left, DFS node.left, passing in the two nodes that we defined. If it is true, let's call it 1 for now. And if it's not true, we'll give it the value of 0. Same thing for the right. If it exists in the right subtree, we give it a value of 1, else we give it a value of 0. Finally, let's make sure that if it's the node itself, so if node equals P or node equals Q, give it a value of 1 or 0. So once again, this is to check the left subtree, this is to check the right subtree, and this is to check if the node that we're passing is one of the nodes that we're trying to find. And we can say if left plus right plus mid is greater than or equal to 2, we just mark that as the answer. Why? Because once again, we're trying to find the LCA of two given nodes. So if any of these two return as true, then that means that we can define it as an ancestor of those two nodes. As for the return function of our recursive call, you can say that we can return mid plus right plus left is greater than 0. Why? Because if any of these three conditions returns true, that means that the subtree has the node. So let's invoke this and return the answer, and let's see if this works. Works just fine. Works just fine. Cool. So runtime, we're doing a DFS, but this is just O of n. So n is the number of nodes in our binary tree. And that's just about it. So once again, just to summarize, these three statements are to check whether the node exists in the left, right, or in the left subtree or right subtree, or is the node itself. This is to check whether we found both nodes to make sure it's greater than or equal to 2. And finally, this is the answer to the recursive call for here, where we just check even deeper if those smaller subtrees have the nodes themselves or are the nodes. So with that, I'll put a link to the question as well as my GitHub down below, and I'll see you guys next time.